Hello students, welcome to the class. So in this lecture, we will focus on section 8.7.6 to 8.7.7 of NCERT chapter 8, Organic Chemistry, some basic principle and techniques. This is disclaimer. Now in this class, you will be able to understand the influence of electronic displacement on structure and reactivity of organic compounds. Now in this objective, we have already covered one of the electronic displacement, which is inductive effect. Now in this class, according to the NCERT, we will cover the section 8.7.6, which is resonance structure, and after understanding this resonance structure, we will move on to one of the electronic displacement, which is resonance effect. We already know there are three types of permanent electronic displacements. First is inductive, second is resonance, and the third is hyperconjugation. Now the temporary electronic displacement consists of electromeric effect, but our today's focus will be on resonance effect. Now first, let us try to understand what is resonance. If I tell it in simpler terms, then it is delocalization of pi electrons within a molecule or ion. Now this is the most distinguishing part between resonance and inductive effect. In inductive effect, the delocalization occurs for the sigma electrons, but here delocalization is of pi electrons. And I would not say the word delocalization for sigma, because that is a kind of small movement of electron, but not the complete delocalization. Here the electrons are completely delocalized from their previous position. But what is the reason we used this term resonance? At what point of time we have faced the limitations of single Lewis structure? Let us move on to that. Now it is seen that for most of the molecules, especially those containing pi bonds or pi electrons, their properties cannot be explained by a single Lewis structure. For example, benzene can have two different structures. Now they both are identical in terms of connectivity, but if you consider it for suppose carbon 1 and carbon 6, so here carbon 1 and carbon 6 is joined by the single bond in the structure number 1, whereas in the structure number 2, carbon 1 and carbon 6 are joined by double bond. Now these both are valid Lewis structure, no confusion in that. But what it is seen, if you go through the prediction of this Lewis structure, then the structure number 1 and the structure number 2 both are incapable of predicting the actual bond length comparison. So according to these two structures, it is obvious that the C1-C2 bond and the C1-C6 bond will be of different length. But in reality, it was seen that in case of benzene, all bonds between carbon are of same length. So this was quite striking. Now to explain this, what we did, we introduced the term resonance. If I tell it in simpler terms in case of benzene, then it is what? It is your equal delocalization of electron due to pi electron movement, which is called as resonance. Okay, so here due to that uniform distribution, we are seeing what? Equal bond length. Now we will see that how is this delocalization of pi electron occurring and what is the criteria for the delocalization. So we will start with now conditions for resonance. Here is a structure for benzene. Now two structures are given here. In the first case we have p orbitals, and in the second case we have the electron clouds. Now the basic condition for your electrons to participate in resonance is that it should be a planar molecule, and for that each and every carbon should be sp or sp2 hybridized. So if you consider a benzene Lewis structure, then you will quickly recognize that all the carbons are sp2 hybridized. So this is the first condition for resonance. Moving on to the second one. Now if this is true, Then the second thing is all the p orbitals should be parallel to each other for their proper overlap. You know what is side on side overlap, and for side on side overlap, the orbitals should be parallel to each other. In this case, your parallel p orbitals will overlap with each other, and that will result in a conjugated system. Okay, how do we show that conjugated system? Through orbital diagram. You can see that we have a blue disk sandwiched between two lobes of pink clouds. Okay, now these two pink clouds are donating electron density that are hovering over the carbon atoms, right? So this is the resultant of sidewise overlapping of p orbital. I hope you are getting my point. Okay, now moving on further, this is the basic criteria. So remember this. Now this is the, I would say, the structural pattern that you should remember for every molecule to undergo resonance. Okay, their p orbital should be available for sidewise overlapping. But we need some convenient method to represent this complex orbital structure. So we will introduce you with some rules for writing the resonance structure. The first and the most important rule: your atoms will never move if you have two different resonating structures. What will move? Only the lone pairs and the pi electrons. Okay, means the electrons that are present in the pi bond or those which are present in as the lone pair. So they will only shift. For example, if you consider benzene, then the carbon and hydrogen are intact in their place, whereas the double bonds are moving. You can see here, if you look on the left and the right structure, you can clearly see that the double bond is moving from here to here, okay, in a circular pattern. But the carbons and hydrogens, they are intact in their place. Second thing, the number of electrons will not change if you are considering two different resonating structures. That means you are considering the valence electron. Of course, the inner core electrons is impossible to change in a way, I would say, but the valence electron will also be constant. Their count will also be constant for two different resonating structure of the same molecule. For example, if you take the carboxylate ion, which is CO3 2-, it has a total number of 16 valence electrons. Now, if you draw the three resonating structure of this carboxylate ion, which is being drawn here with the help of arrows. Okay, now going back to your previous memories, you must remember what these arrows are representing. So the tail of the arrow is donating the source of the electron, and the head of the arrow is representing where this source is sinking its electron or moving its electron. So here you can see that the electrons are moving with the help of arrows from here to there. Now this movement is only changing the position of electrons, but not the total overall count of electrons. At the same time, if you verify it for the first rule, you can clearly see that carbon and hydrogens are also not changing their position. I hope you are getting my point. Okay. Now, if you remember these two important rules, we can have different types of resonating structures. So here is a list of that. Okay, I have also represented the same with the help of simply dot and bond structure. So this is just for your simplification, or either you can use the actual structure. Now we will see each of these structures undergoing resonance. Starting with the first one, which is pi bond resonance. We will consider the CH2 double bond CH, single bond CH, double bond CH2 molecule for this case. Now, what can probably happen? If you look for the 4 carbons here, all of these 4 carbons are sp2 hybridized. So this thing is for sure. So the first condition for resonance is being verified. What about the second condition? There should be the presence of parallel p orbital. Of course, one pure p orbital will be present which will not undergo hybridization, and that will help in overlapping and movement of electron. Here the double bond is moving from right on to left, okay? And from where it is moving, at that point we are seeing a positive sign. And the sink where the electron is going, at the left extreme, there you will see a negative sign accumulated on the terminal carbon. Moving on to the next one, we can have a pi bond and a lone pair resonance. Now here, if you look upon NH2, okay, the nitrogen is not sp3 hybridized, but still it can undergo resonance, okay. So that condition that you have seen earlier, it is likely applicable for carbon, not for other heteroatoms. Now what will happen in the resonating structure? The lone pair on the nitrogen will resonate onto the single bond, and that will affect the double bond, which will move on to the next carbon, creating a carboanion, whereas the nitrogen which is releasing its electron will get a positive charge. Moving on to the third type. The third type is kind of interesting. It is pi bond and radical resonance. Hope we have discussed a lot about this radical in the homolytic cleavage. Now we will see that how this radical can be stabilized. For that, we have a structure where we have a double bond and a single bond, then we have a radical. The most probable outcome can be that your radical can pair up with the pi electron, one of the pi electron, and the other pi electron will move on to CH2, creating a radical on the left extreme carbon. Although these two structures are electronically same, but still the electrons are moving, okay, you can see it very clearly. Moving on to the next type of resonance, we have pi bond positive charge resonance. Now in place of radical, we will simply place a carbocation. How will it resonate? So the double bond will move from left to right, and that will create a vacuum onto the extreme left carbon, resulting in a carbocation formation. Now can you see a pattern here? In the movement of the electron, can you see a pattern? Yes, of course there is a pattern. The electrons are always moving from a electron rich site to a electron deficient site. Okay, you can look for it in the lone pair bond pair, you can look for it in the bond pair positive charge resonance, and you can look for it in the pi bond and the radical. Similarly, if you look upon the pi bond and the negative charge resonance, and for that we are considering double bond, single bond and negative charge. Here also you can see that the negative charge is the one which is donating electron, because in comparison to the double bond, the negative charge has a higher electron density. So the negative charge will moved on to that single bond, and that will result in the movement of double bond onto the extreme left carbon, creating a carboanion. Right? So these are the 5 types of resonance that are possible. What are those? If I name them again, so we have pi bond, then we have pi bond lone pair, then we have pi bond radical and pi bond positive charge, and lastly we have pi bond negative charge. So if you thought about this flow of electron, now we can just generalize it with the help of examples. Now in doing so, remember one very important line. Electrons will always flow from a region of higher electron density to a region of lower electron density. For example, if we take a heterocyclic aromatic compound, which is a 5-membered ring containing 4 carbon and 1 sulfur, the electrons are moving on from the sulfur, that is the lone pair, okay, and it is moving throughout the ring, and at last it is coming on to the ring. Now what can you notice here? That the electron rich area, which is sulfur, which is accumulated with lone pair, that is the one responsible for moving the electron or flowing the electron throughout the ring. And the electron is moving to a region where there is a lower resonating structure. Now this structure that you are seeing is the resonance structure of thiopene. One very important point, although you have learnt about this in the previous classes of chemical bonding, But you should remember here also that two resonating structures are separated by a double-headed arrow. You can see for it in each and every structure, between each and every structure. Moving on to the next example. Here I have taken a benzene. Onto the benzene we have a methoxy group attached, OCH3. Now the oxygen is capable of donating electrons and that is moving again throughout the ring. Upon the first donation of oxygen's lone pair onto the carbon, a double bond is introduced between carbon and oxygen, and since oxygen is losing its electron, so it is getting a positive charge. In place of that, the double bond next to it is moving on to the carbon, creating a negative charge. If I ask you what kind of resonance it is out of the 5 types, so it is a lone pair bond pair type. The previous one was also the example of lone pair and a bond pair type. Again, the electron will rotate throughout the structure and at last it will go on to the oxygen, go back to the oxygen. Moving on further. Now we will see stability of resonating structure. You have seen various resonating structures are possible in different conditions. But the important part is that which one is the most stable one. Okay, so that is the question now. So starting with the first rule, so I will list you some rules and you will follow them in chronicle order. The first one is number of pi bonds. According to this rule, the structure with more pi bonds are generally more stable. Let's look on to two structures. Here you can see that the first structure is having 1 pi bond, whereas the second structure is having 2 pi bonds. Okay. So which one will be more stable according to the rule number 1? Of course, the structure number 2 will be more stable than the structure number 1. What I meant by the chronicle order, if you see that the first rule is followed and from the first rule itself you are getting the stability order, you will not move on to the second rule. So that's a cut point to it. Moving on to the next rule, we have the octet rule. According to this rule, the structure that are having a complete octet is more stable to those which are having an incomplete octet. Here you can see an example of it. You can clearly see that the oxygen's lone pair are resonating to create a next structure. But what can be inferred from here? It can be clearly seen that the structure number 2 is having a complete octet in comparison to the structure number 1. So, structure number 2 is more stable. Moving on to the next one. Next we have charge. Okay, so in case both of the structures are having a complete octet, then in that case we will move on to the third thing, which is charge. It is seen that neutral structures are more stable than the charged one. If you look upon structure number 1 and structure number 2, they have a charged species. Okay, the second one is charged. So the second one will be least stable. Now one more thing. Okay, so this is incorrect in a way to look upon the rule number 3, but for example we are taking this, but you can decide the stability from the first rule itself. The one with the greater number of double bonds is more stable, and here you can clearly depict that structure number 1 is stable from the rule number 1. You do not need to move on to rule number 3, but still there are cases where the number of pi bonds are equal. In those cases you will follow this charge rule. Okay, now moving on to the stability. Of course, the structure number 1 is more stable than the structure number 2. Then next, rule number 4 is charge placement. Suppose two species are having charge. So in that case, the one which is having a negative charge on an electronegative element will be more stable, and a positive charge on a more electropositive atom will be more stable. Clear? Means the negative charge will be on electronegative element and the positive charge will be on the electropositive element. If you consider structure number 1 and structure number 2, you can see it clearly in the structure number 1 that the negative charge is on carbon, whereas the structure number 2, the negative charge is on oxygen. So we can say that the structure number 2 is more stable. What about rule number 1, 2 and 3? So rule 1 is equally applicable to both of them because they have the same number of bond. Rule number 2 is also equally applicable. Similarly, they both are charged. So you have to move on to rule 4 to decide their stability. Therefore, the stability of 2 is more than 1. Moving on to the next. Last, we have this distance rule. Suppose the negative charge is present on electronegative element and the positive charge is present on electropositive element in both the given structure. Then in that case, you should remember that like charges should be placed far from each other to overcome repulsion, because less is the repulsion, more is the stability. Similarly, the opposite charges should be closer to each other, and that one will result in a more stable resonating structure. Let us see the last point, which is equivalent resonating structure. Now, apart from these 5 rules, we have a master rule. What is that? It is known as equivalent resonating structure. Suppose there is a structure which makes equal contribution to the hybrid. Now here a new term is being introduced known as hybrid. So this is actually used for a symbolic representation for actual structure. So multiple resonating structure are possible for the same molecule, and none of them is able to clearly specify the actual structure. In that case, you take a resonance hybrid, and that is not the actual structure but a symbolic representation of the actual structure. Now it is seen that the equivalent resonating structure make equal contribution to this actual structure or hybrid structure. For example, if you take carboxylate ion, it can exist in 2 resonating forms. Both of these resonating forms are equally stable in terms of electronic distribution. Okay, you can see here that if one oxygen is doubly bonded, the other one is negatively charged, and that can be seen opposite in the case of the second resonating structure. Therefore, the stability of 1 and 2 is same and they are highly stable. So that also results in a higher stability if 2 resonating structures are of the same form. So this kind of equivalent resonating structure can be seen in various molecules. For example, in case of benzene also it is seen. Okay, you must have seen in the case of benzene that the double bond and the single bond are distributed in such a way in 2 structures that the electronic representation is same. So we will do some examples to validate these rules. Moving on to the example number 1. Here we have 2 resonating structures, 1 and 2. Starting with the rule number 1, so we will obviously apply the first rule. We have to count the number of bonds. In the first structure, the number of bond is 8, including the sigma and pi bonds. Whereas in the second structure, the number of bond is 7. Therefore, from the rule number 1 itself, it is clearly depictable that the stability of 1 is greater than 2. Moving on to the next one. If the rule number 1 is suppose not applied, it is not applied or it is equally applicable to both of them, then what you will do? You will move on to the rule number 2. Suppose in these 2 structures, the number of bonds are equal. Now, how you will decide the stability? So, both have the same number of bonds and the octet of each element in both structures are also complete. If you count the number of electrons, then nitrogen has 8 electrons. Similarly, oxygen has 8 electrons in both structure 1 and 2. So, this is also equally applicable to both of them. Their stability cannot be decided further. What about rule number 3? Again, both species are charged. So this can also not be the deciding factor for their stability. In the first one, the nitrogen is charged. In the second one, oxygen is charged. But if you look onto the rule number 4, then you can clearly say that oxygen is more electronegative than nitrogen. So where will the negative charge lie? It will lie on oxygen for more stable structure. Therefore, structure number 2 is more stable than structure number 1. I hope you are getting my point. Moving on further. Now we have example number 3. So these are the 3 possible resonating structure of aniline. Okay, here is a benzene and NH2 group is attached to that benzene. And these three structures are possible for this aniline structure. Which one is the most stable? Of course, the rule 1 and the rule 2 is same for all three structures. Both have the complete octet and both have the same number of bonds. But structure 1 is more stable than the structure number 2 and 3. What is the reason behind it? Can you think of it? So for that you have to move upon rule 3. So structure 1 is having no charge on it, whereas the structure number 2 and 3 are charged species. So that is the reason structure number 1 is more stable than 2 and 3. Now we have to decide the stability order between 2 and 3. How you will do it? Now if I consider rule number 3, then according to rule number 3, both are unstable. Both structure number 2 and 3 are unstable. Why is it so? Because the negative charge is on a less electronegative element, which is carbon, and the positive charge is on a more electronegative element, which is nitrogen. Therefore, due to this reason, both structure 2 and 3 are equally unstable. Moving on to the last number rule, which is rule number 5. From rule number 5, it is clearly seen that structure 2 is more stable than structure number 1. Structure number 3. Why we are saying it? Because there are two charges and these two are opposite charges. In structure number 2, these opposite charges are in close proximity. In close proximity. Whereas in structure number 3, they are at a greater distance. Due to this reason, the structure number 2 is stable than the structure number 3. Okay. I hope you are getting my point. Now moving on to a very important concept named as resonance energy. Now to understand this, you have to remember what I told about this resonance hybrid. Do you remember it? Okay, so let me clarify it for you. So the resonance energy is the energy difference between the most stable resonating structure and the resonance hybrid. What was your resonant hybrid? It was a hypothetical resemblance of the actual structure. To understand this, we can write it in the mathematical form also. Resonance energy is equals to energy of resonance hybrid minus the energy of most stable resonance structure. Now, you can see the same in this graph also. Here, the most stable resonating structure of benzene, which is being written here, is at an energy of 150.624 kilojoule per mole. Okay? Or 36 kilocalorie per mole. In comparison to that, our actual structure or the hypothetical representation of actual structure, which is hybrid structure of benzene, is at a lower energy. Okay? And the difference between their energies, these two energies, is named as resonance energy. So you will remember this. Okay. A takeaway point for you. Remember that this resonance hybrid has no real existence. It is just a resemblance. So you know that electron are being delocalized continuously. To represent this conjugation, rather than representing the electrons on one point, we have made a circle representing that electron is being distributed equally to all of these 6 carbons. Okay. Moving on to the next one, we have types of resonance effect. Okay, so we have talked a lot about this resonance. Now we will specify the types of resonance effect. Now this helps us in knowing the electron shift, and that is the reason we see reactions, because if there is an electron shift, there will be increase in polarity in the molecule, and that will result in reactivity as well. Now similar to the inductive effect, there are two types of resonance effect. First is positive resonance effect, which is plus R. Of course, it is donation of electrons, similar to that inductive effect. And next we have negative resonance effect, where the group is capable of accepting or taking the electron, which is named as minus R effect. So let's start with the first one, positive resonance effect or plus R. If your group is donating electrons by a conjugated system, then we call that electron donating group as showing plus R effect. And they donate electrons to the system. For example, we have OH group, which is hydroxyl, then we have amine group, which is NH2, then we have OR, which is alkoxy. Suppose we take the example of NH2. Here, the lone pair of nitrogen will move on to the benzene. Now, where is this flow coming from? Remember, we have talked about the electron flow. The electron always moves from a higher electron density to a lower electron density, and the lone pair is a region of higher electron density. So the electron will move start moving from NH2 and move on to the carbon. That will deliberately move the electron pair throughout the ring and will bring back to the nitrogen itself. So what is this nitrogen doing? It is donating its electron and creating a negative charge on certain carbons with respect to the nitrogen. So this is in a way increasing the electron density onto the benzene. Therefore, NH2 is a electron donating group and it shows plus R effect. Moving on to the next type. Next we have negative resonance effect, which is denoted by minus R. So there are some groups which are called as electron withdrawing group, and if they are attached to a conjugated system, they will withdraw electrons from the system. For example, we have NO2, we have CN, we have aldehydic group, then we have carboxylic group. Suppose we take an example of nitro group attached to the benzene again. Here, the double bond is being moved on between carbon and nitrogen. So you are creating a positive charge on benzene in this process. That means you are making benzene electron deficient due to the attachment of this nitro group in the benzene. Therefore, this nitro group is an example of negative resonance effect and it shows minus R effect. So let us summarize all of these today's discussion in one short note. So first we started with resonance. So it describes the delocalization of pi electrons with a molecule or ion. Then we talked about the condition for resonance in case of carbon. The first one is the carbon should be sp or sp2 hybridized. The second one is the p orbital should be present parallel to each other so that the overlap can be possible, and that will result in a complete conjugated system in the molecule. Okay. Then moving on further. Next we have resonance energy. What is resonance energy? It is the difference in energy between the energy of resonance hybrid and the energy of most stable resonance structure. So what is resonance hybrid? So it is basically this energy of actual structure. Here the resonance hybrid is a term used as a resemblance for the actual structure. What are the rules for writing the resonating structure? First, the atoms will never move. Second, the total number of valence electrons will remain constant. Then we talked about the types of resonating structures. There we have 5 fragments: double bond, single bond, double bond, single bond, lone pair, double bond, single bond, radical, then double bond, single bond, positive charge, and double bond, single bond, negative charge. Now one thing is common in all of this, which is double bond, single bond. Okay. Next part is just a variable. So either it can be double bond, which is again transform onto a lone pair, then it can be a radical, then it can be a positive charge, or it can be a negative charge. After that, we talked about rules that are useful in deciding the stability of resonating structure, and they should be followed in chronicle order. The first one is a structure with a greater number of bonds are generally more stable. Rule number 2, structures that satisfy the octet rule are more stable. Then neutral structures are more stable than the charged ones. Rule number 4, negative charges are more stable on electronegative atoms and positive charges are more stable on electropositive element. The last one, if you have both positive and negative charge or positive or negative charge, then the opposite charges should be present closer to each other, whereas the same charges should be present as far from each other. So this was all for today's lecture. I hope you enjoyed the session. Thank you for joining it.